Here we start our module, transmission lines, waveguides and cavity resonators. So, first of all, we discuss about transmission lines. Transmission lines are waveguides. They are double conductor waveguides. In the next session, we will discuss about waveguides in detail, other type of waveguides other than transmission lines also. So in our previous sessions, we have seen that electromagnetic source produces electromagnetic waves. So now consider an isotropic and omnidirectional source that generates waves in all directions. So such a source radiates the electromagnetic waves in all directions. This is isotropic too. So same type of waves is being transmitted to all directions. So even though we use a highly directive antenna, the antenna you see already that radiates electromagnetic waves in one direction. But the energy spreads over a wide area at large distance. So this is radiated and large distances the energy is being spread. So that means this radiated energy is not guided. So therefore the transmission of power from the source to the receiver is not efficient. That means we will not get all the power transmitted to the receiver. Only a part is being received at the receiver and rest are being used. So the efficiency of reception of the signal is low. So the transmission of power and information signals from the source to the receiver is inefficient. And also we have to use antennas of the order of wavelength. The size of the antenna is of the order of lambda by 2. So if we are using very low frequency signals, then the wavelength is very large. So we have to use a very large antenna to propagate the signals. So for example, the AM broadcast station, that is the amplitude modulated case, the size of the antenna is of the order of a few hundreds of meters. So even if we are transmitting the very low frequency signals, 50 Hz signals, then the wavelength should be of the order of C by 50. Right. So that is equal to 6 into 10 to the power 6 meters. This much long. So this is impossible. So the size of the antenna should be comparable to the wavelength for the efficient transmission. So we cannot construct antennas of this height. So for the efficient transmission of power or information signal, we use waveguides. So they are waveguiding structures, and transmission lines are a type of waveguides. So transmission lines are waveguiding structures that allow transverse electromagnetic waves to pass through. They are waveguiding structures. They are waveguides that allow transverse electromagnetic waves to pass through. So all other waveguides, simple conductor waveguides, will not allow transverse electromagnetic waves to pass through. So for the efficient transmission of power and information signal, the source energy should be directed or guided. So this is done by waveguides, and the transmission lines are special types of waveguide that have two conductors in it. So these transmission lines allow transverse electromagnetic waves to pass through. Transverse electromagnetic waves means both E and H are perpendicular to the direction of propagation, and they are perpendicular to each other. The electric and magnetic field are perpendicular to each other, and both are perpendicular to the direction of propagation along the guiding line. So in the next part of this module, we discuss about the single conductor waveguides, but they will not pass transverse electromagnetic waves through them. So now we discuss the three types of transmission lines. So these are the most common types of guiding structures that support TEM. So transmission lines only support transverse electromagnetic waves to pass through. So the general types of transmission lines are: one is parallel plate transmission line, second is two-wire transmission line, and third one is coaxial transmission line. So all these transmission lines are the wave guiding structures or waveguides that support TEM. So out of this, the parallel plate transmission line is a type of transmission line that consists of two parallel conducting plates separated by a dielectric slab of uniform thickness. So at microwave frequencies, this parallel plate transmission lines can be fabricated on a printed circuit board. So they are called strip lines. So നമുക്ക് PCB printed circuit boards fabricate ചെയ്യാം. രണ്ട് കണ്ടക്ടേഴ്സ് അതിനടുത്ത് ഒരു dielectric, and they are called strip lines. So now the two-wire transmission line consists of a pair of parallel conducting wires separated by a uniform distance. So examples are power and telephone lines in rural areas, and the lines from a rooftop antenna to a television receiver, etc. So the next one is the coaxial transmission line. So this consists of an inner conductor and a coaxial outer conducting sheet separated by a dielectric medium. These coaxial lines confine the electric and magnetic fields entirely within the dielectric region. So no external noise or stray fields are generated by the coaxial transmission line. So there is not much noise over here, and examples include telephone and TV cables, and input cables to the measuring instruments like CRO. So the transmission lines can support other modes like TE mode, transverse electric, transverse magnetic, etc. So we will discuss about this in the next part of this module. So transmission lines can support TEM, TE, TM, while the other single conductor waveguides can support TE and TM alone. So now we discuss the transverse electromagnetic waves along a parallel plate transmission line. So now here we consider a transverse electromagnetic wave, TEM wave, which is propagating along positive z direction. So let the polarization of the wave, that means the electric field of the wave is along y direction and the magnetic field is along x direction. So now this figure shows the cross-section of such a transmission line. So this is taken as y-axis, and this direction is taken as x-axis, and this direction is taken as z-axis. So, ഈ പാത്തിൽ ഇങ്ങനെ എക്സ്റ്റെൻഡ് ചെയ്ത് പോവാണ്. ഇതിന്റെ ഒരു ക്രോസ് സെക്ഷൻ ആണ് എടുത്തിരിക്കുന്നത് കേട്ടോ. ദ ഡിറക്ഷനിലാണ് വേവ് പ്രൊപ്പഗേറ്റ് ചെയ്യുന്നത്. സോ ഇറ്റ് ഈസ് ഹാവിംഗ് എ വെരി ലാർജ് ഡയമെൻഷൻ. So we consider a very long transmission line. So dimension of along z-axis is very long. So this is just a cross section only. So and the electric field is along y direction. The magnetic field is along x direction. Let W as the width of the transmission line and D as the separation distance between the two parallel plates. And the length is a very large quantity. In a parallel plate transmission line, we have to write the time harmonic and source free wave equation. So the time harmonic case, it is just the Helmholtz equation. Del square E plus k square E is equal to 0. So in terms of the propagation constant gamma, which is jk, this can be written as del square E minus gamma square E equal to 0. So we have discussed this equation in our offline classes in detail. So the solution of this equation for a wave propagating along z direction is given by, so the electric field is along y direction, Ay cap Ey. So Ey is E0 e to the power minus gamma z. So the wave is propagating along z direction, so we have e to the power minus gamma z. And the wave is polarized along y direction, so we have the electric field along y axis. And therefore the magnetic field is given by, it is equal to 1 over eta An cross E. An is the propagation direction. Here it is AZ. AZ cross E. So 1 over eta AZ cross Ay cap E0 e to the power minus gamma z. AZ cross Ay is minus X. So minus X cap E0 by eta e to the power minus gamma z. So which can be written as Ax cap Hx, where Hx is equal to minus E0 by eta e to the power minus gamma z. So here gamma is the propagation constant and eta is the intrinsic impedance of the dielectric medium. So now we assume that the conducting plates are perfect. They are perfect conductors, sigma infinity, and the region in between the plates, that means the dielectric medium, is a perfect insulator, sigma equal to 0. So this is a lossless dielectric medium. So for a lossless medium, we know that Kc is K itself, and therefore gamma is equal to J beta alone. So we know that gamma is equal to alpha plus J beta for a lossy medium, and for a lossless medium alpha is equal to 0. So J beta or J omega root mu epsilon. And we know that the intrinsic impedance for a lossless medium is purely real, and it is equal to root of mu by epsilon. Now we have to consider the boundary conditions to be satisfied at the interface between the dielectric and the conducting plates. The boundary condition here and the boundary condition here. So this is an interface between a conductor and a perfect dielectric, and this is also an interface between a perfect conductor and a perfect insulator. So for that we have to remember the boundary conditions at the interface between a dielectric and a perfect conductor. We have studied this already in our module 1. These are the boundary conditions in the interface between a dielectric and a perfect conductor. So the perfect conductor is considered as medium 2 here. So inside the perfect conductor, we know that the electric and magnetic fields are zeros. And therefore, the boundary condition will become E1t equal to 0, AN2 cross H1 as Js, and AN2 dot D1 is rho s, and V1 normal equal to 0. So, but here we are writing the boundary conditions in terms of E and X. So, we have seen E1 tangential is equal to 0 and V1 normal equal to 0. So, when V1 normal equal to 0, H1 normal is equal to V1 normal by mu, which is also equal to 0. So, at the boundaries, E1 tangential and H1 normal should be equal to 0. So, this one is x-axis, this one is z-axis, and this one is y-axis. This point is chosen as the origin of the coordinate system. So, this lower conducting plate corresponds to y equal to 0, and the upper conducting plate corresponds to y equal to d. So, y equal to 0 and y equal to d. So, these are the boundaries. So, the boundary conditions are to be satisfied at the boundaries. So, at the boundary y equal to 0, E1 tangential and H1 normal are zeros. So, that means at this point, the tangential components means the tangential components to the conducting plate or interface. So, the interface is along xz plane. So, it is having an equation y equal to 0. So, the tangential components corresponds to x and y components, and normal components corresponds to the y component. So, Ex is 0 and Ez are 0. Electric field exists only along y direction. So, the tangential components are zeros for y equal to 0 and also for y equal to d. And the normal component of magnetic field. Normal component of magnetic field means Hy. Hy is already 0 because the magnetic field exists only along x direction. So, for the lower and the upper conducting plates, that means for the two boundaries, E1 tangential and H1 normal are zeros. That means Ex is equal to 0, Ez equal to 0, and Hy is equal to 0. So, those boundary conditions are satisfied for the lower and upper conducting plates. So, these equations are satisfied for y equal to 0 and y equal to d, since Ey equal to Ex equal to 0. That means tangential component is equal to 0 and Hy equal to 0. So, now we have to look the other two boundary conditions for the two conducting plates. So, first of all, for the lower conducting plate, y equal to 0. So, we have to consider the boundary condition AN2 dot D equal to 0. AN2 is the outward normal from medium 2 into the medium 1. So, here the perfect conductor is taken as medium 2 and the dielectric medium as medium 1. So, then the outward normal from medium 2 into medium 1. Lower conducting plate ഈ conductor ഇതിനകത്ത്. So, this is along y direction. So, AN2 is AY for the lower conducting plate. Upper conducting plate medium 2 to medium 1 minus AY. So, you have to remember that also. So, the boundary conditions AN2 dot D equal to rho S. So, we have to apply this for the lower conducting plate. AN2 is AY. AY cap dot D. So, for the lower conducting plate, the surface charge density is written as rho s L. And for the upper conducting plate, the surface charge density is written as rho s U. And this is for the lower conducting plate y equal to 0. So the expression becomes ay cap dot d is equal to rho s L. So d is epsilon e. So ay cap dot epsilon e. E is again ay cap e0 e to the power minus gamma z. So this is equal to rho SL. So ay cap dot ay cap is 1. So this is epsilon e0 e to the power minus gamma z. So rho SL is equal to in the lossy dielectric medium, gamma can be written as J beta. Epsilon E0 e to the power minus J beta Z. Similarly, the other boundary condition, AM2 cross H1 is equal to JS. So instead of H1, we take H. Because the electric field and magnetic field exist only between the plates. In the conducting plates, the electric and magnetic fields are 0. In between them, the electric and magnetic field exist. So AM2 is AY itself. AY cross H is equal to JS. And for a lower conducting plate, JS is taken as JSL. The surface current density of the lower conducting plate, and for the upper conducting plate it is JSU. So JSL. So AY cross H is equal to minus AX E0 by eta e to the power minus gamma z. So this is equal to JSL. So AY cross X is minus AZ, minus AZ is plus AZ. So JSL is equal to AZ cap E0 by eta e to the power gamma z, which can be written as e to the power minus j beta z. So minus E0 by eta e to the power gamma z is Hx. So this is minus AZ cap Hx where Hx is equal to minus A0 by eta e to the power minus gamma z. Okay. Similarly, we can write the boundary condition for the upper conducting plate y equal to d. So for the upper conducting plate, we have seen that the outward normal from the conductor to the dielectric medium is along negative y direction. So we have minus ay dot d is equal to rho su, or rho is equal to d is epsilon ey. So minus epsilon e0 e to the power minus j beta z. There is a minus over here. And similarly, minus ay cross h is equal to JSU, or we can write JSU is equal to, so you can do the same procedure, but there is a change in sign over here. So we have minus AZ cap E0 by eta e to the power minus j beta z. So in terms of Hx, it can be written as AZ cap Hx. So thus rho SL, rho SU, JSL and JSU give the expressions for the surface charge and surface current densities for the lower and upper conducting plates. So from these equations, we can see that this rho SU, rho SL, JSU, JSL depends on e to the power minus j beta z. That means this vary sinusoidally with Z. So these are the sources. So since the sources vary sinusoidally with Z, the corresponding field Ey and Hx also vary sinusoidally with Z. So this is illustrated in this figure. You can see that the charge densities vary sinusoidally. So cosine wave ആണ് maximum here decreases. So അടുത്തടുത്ത് വരുമ്പോൾ ഇവിടെ ഡെൻസിറ്റി ചാർജ് ഡെൻസിറ്റി കൂടുതലായിരിക്കും. ഈ റീജിയൻ ചാർജ് ഡെൻസിറ്റി കുറവാണ്, എന്നിട്ട് നെഗറ്റീവ്. So maximum here, minimum here. So maximum, minimum, then 0, negative, negative maximum. അതുപോലെ cosine wave പോലെ വേരി ചെയ്യും. അതുപോലെ ഇവിടെ JS കണ്ടക്ടിങ് പ്ലേറ്റിനകത്താണ് JX ഇവിടെ മാക്സിമം. വലിയ ആരോ ആകുമ്പോൾ മാക്സിമം ഡിക്രീസ് ചെയ്യുന്നു, 0 ആവുന്നു, ഓപ്പോസിറ്റ് ഡയറക്ഷനിൽ മാക്സിമം ആവുന്നു, മിനിമം ആവുന്നു. സോ അതുപോലെ ലോവർ കണ്ടക്ടിങ്ങിനും അപ്പർ കണ്ടക്ടിങ് പ്ലേറ്റ്. So the corresponding electric field the y directionലാണ് കാണിച്ചിരിക്കുന്നത്. Electric field maximum here. So the lines are closer electric field lines. So maximum ഇവിടെ അത് ഡെൻസിറ്റി കുറയുമ്പോൾ അത് മിനിമം ആകും. ലൈൻസിന്റെ 0 ആകുന്നു, ഓപ്പോസിറ്റ് ഡിറക്ഷൻ മാക്സിമം. മാഗ്നറ്റിക് ഫീൽഡ് എക്സ് ഡിറക്ഷനിലാണ്, ഇതിന് പെർപെൻഡിക്കുലർ ആണ്. ഇവിടെ മാക്സിമം കൂടുതൽ ഇന്റൻസിറ്റി കാണിച്ചിട്ടുണ്ട്. Decreases when it becomes 0 and increases with the maximum in the opposite direction into the plane. Okay, so the charge densities, current densities, electric fields and magnetic fields and the transmission lines vary sinusoidally with respect to Z. So all represent cosine waves. ഇവിടെ YZ പ്ലെയിൻ ആണ് പ്ലോട്ട് ചെയ്തിരിക്കുന്നത്. പ്രൊപ്പഗേഷൻ ഇങ്ങോട്ട്, Y ഇങ്ങോട്ട്, ഇലക്ട്രിക് ഫീൽഡ് ഇങ്ങോട്ട്, മാഗ്നറ്റിക് ഫീൽഡ് രണ്ടിനും പെർപെൻഡിക്കുലർ ആയിട്ടുള്ള ഡയറക്ഷൻ കാണിച്ചിട്ടുണ്ട്. Since we are considering prime harmonics equation, we can express the Maxwell equations in the Phasor form. So they're given by the Maxwell curl equations are given by del cross E is equal to minus j omega mu h and del cross H is equal to j omega epsilon E or time harmonic equation. So where E and H are phasors. So we know that the electric field is along y direction, AY, EY, and the magnetic field is along x direction, AX, HX. HX is a negative quantity here. So, but del cross E is having only y component, and we can see that it is just AXAY is it. We have used AXAY is it instead of IJK. So AX cap dou EY by dou Z. And there will be a dou EY by dou X term also. But we know that EY is a function of Z alone. EY is E0 e to the power minus gamma Z for a uniform plane wave. This term also vanishes. And since EY is a function of Z alone, dou by dou Z can be written as d by dz. The partial derivative can be written in terms of the ordinary derivative. There is a negative sign over here. Minus plus. So del cross E is equal to minus j omega mu h reads minus x cap dEy by dz is equal to minus j omega mu hx. It is hx ax alone. So we have the negative signs cancelled and ax also cancelled, and we have dEy by dz is equal to j omega mu hx. This is equation number 1. So similarly we can write the other curl equation. Del cross H is equal to j omega epsilon E as dHx by dz is equal to j omega epsilon Ey. So this one is termed as equation number 2. So now we have to integrate equation number 1 over y from 0 to d. Integrating equation number 1 from 0 to d over y, we get d by dz of integral 0 to d. The derivative is taken out. The derivative is with respect to z, and we are integrating with respect to y. Equal to j omega mu integral 0 to d hx dy. So here we are integrating from 0 to d, from lower plate to upper plate. So Ey as a function of z alone and can be taken out of the integral. So we get d by dz of Ey dy. So dy integrated from 0 to d will give y. Applying the limits, we get d minus 0. J omega mu xx is also independent of y. So xx into d. So now we can write this Ey into d, or integral 0 to d Ey dy in terms of potential difference between the lower and upper place. So we know that the potential difference between 2 points A and B is minus integral a to b E dot dl or E dot dy here. So here it is from 0 to d. For the potential difference between the lower and upper plate, it is integral 0 to d E dy. So this quantity is nothing but we have said the potential difference or the voltage between the upper and lower place. So we can write this expression as d by dz of dz, d of z is equal to j omega mu. So the hx can be substituted in terms of JSU. So we have already found that JSU is equal to AZ cap hx. So here we are using the magnitude of hx. X cap in the equation cut the magnitudes. So hx in the magnitude and it is JSU itself. JSU into D. Okay, so we have now to multiply this expression by the width of the place W, J, and divide it. J omega mu JSU D W by W. We know that W is the width of the plate. JSU is the surface current density. So the surface current density is defined as the current flowing per unit length in a direction perpendicular to the flow of current. So current is flow perpendicular in the direction like current per unit length. JSU. It's even though it's called surface current density, it is current per unit length. We have already defined that. So JSU is I by W. So JSU into W gives the current I of Z. So JSU into W is the current. So we have minus dV by dz. Minus is there. This thing is V of Z. So here we don't have a minus. So this is minus dv by dz is equal to j omega mu d by w into jsu into w. Jsu into w is I of z. The total current flowing in the positive z direction in the upper plate having width w. So, this is of a familiar form. V നമുക്ക് L into di by dt എന്ന് അറിയാം അല്ലേ? നിങ്ങൾ പഠിച്ചിട്ടുണ്ട് minus L into di by dt. So, j omega എന്ന് പറഞ്ഞാൽ നിങ്ങൾക്ക് അറിയാം it is d by dt. So, d by dt of Iz. So, the dimension of this എന്ന് പറയുന്നത് is equal to inductance per unit. So, we know that V is minus L into di by dt minus d by dt of I into L. So, അതേ familiar formula ആണ് V by Z independent. അപ്പോൾ ഈ സംഭവം d by dt equal to. So, this is having a dimension inductance per unit. So, this is equal to L, the inductance per unit length of the transmission line. So, mu into d by w forms the inductance per unit length of the parallel plate transmission line. So, in terms of this L, we can write this equation as minus dv by dz is equal to j omega L I of z. So, this is termed as equation Roman letter 1. So, now we have to integrate equation number 2 over x from 0 to w. Equation number 1, electric field into terminal. So, we have integrated it from 0 to d over y. And equation number 2 gives equal equation for x. So, we have to integrate it over x from 0 to w. From this end to this end. So, we get d by dz of integral 0 to w. Omega w hx dx equal to j omega epsilon integral 0 to w ey dx. So, we have integrated over x from 0 to w. So, x is a function of z alone. So, we can take it out d by dx of hx. Integral dx give x and applying the limit it is w minus 0 w. J omega epsilon ey is also independent of x. It's a constant with respect to x, so it can be taken out of the integral, and integral 0 to w dx give w. Multiply both sides of the equation by a negative sign, we get this. And we know that this hx is equal to having magnitude of jsu. We have already seen this. So, this is the magnitude of hx. So, jsu hx into w means jsu into w. Jsu is the surface current density, current per unit length in a direction perpendicular to the flow of current. So, jxu is actually I by w. Jxu into w gives I. So, this is nothing but d by dz of I of z is equal to minus j omega epsilon. So, we have to multiply this right side of this equation by d by d. Multiplied by d and divided by d. So, ey into d. So, we have already seen that ey into d as negative of dz. So we have done this just before. We have said as this, that is ey into dy, ey minus ey into d as nothing but the potential, minus of potential. So ey into d can be written as minus v of z. So minus minus is plus. So therefore we get d by dz of I of z is equal to j omega epsilon w by d into this ey into d. This negative is it, and this negative is become positive, and yes, so this is minus di by dz. So it is equal to j omega epsilon w by d into v of z. So here this is nothing but the capacitance per unit length, j omega c v of z, where c is equal to epsilon w by d. Then only it is dimensionally correct. So നമുക്കറിയാം ഇവിടെ മൈനസ് ഡി ഐ ബൈ ഡി സെഡ് ആണ്. മൈനസ് ഡി ഐ ബൈ ഡി സെഡ് എന്ന് പറയുമ്പോൾ നിങ്ങൾക്കറിയാം ഐന്റെ എക്സ്പ്രഷൻ നിങ്ങൾക്ക് ഓൾറെഡി അറിയാം, ഡി ക്യൂ ബൈ ഡി ടി, ഡി ക്യൂ ബൈ ഡി ടി. ഒരു ക്യൂവിന് സി വിന്ന് എഴുതുകയാണെങ്കിൽ സി ഇൻറ്റു ഡി വി ബൈ ഡി ടി. So j omega d by dt and dv by dt. So this should be c. ഇവിടെ I മാത്രമല്ല I by z ആയതുകൊണ്ട് this is having a dimension of capacitance per unit length. So here c equal to epsilon w by d is the capacitance per unit length of the parallel plate transmission line. So we have got two quantities, the inductance per unit length and the capacitance per unit length. And in terms of this capacitance per unit length, this is above equation minus di by dz is equal to j omega c into v of z. J omega c into v of z. So this is equation number Roman letter 2. So this equation numbers Roman letter 1 and Roman letter 2 constitute a pair of time harmonic transmission line equations. So this one and this one togetherly form time harmonic transmission line equations. So they rate the phasors I of z and v of z. So minus dvz by dz is equal to j omega li and minus di by dz is equal to j omega cv. You can see that these two equations are coupled, and we can decouple it using equation number 1. We know that I of z is equal to minus 1 over j omega l into dv by dz from equation number Roman letter 1. So substituting this in equation number 2, we get d by dz of I of z. So d by dz of minus d by dz of minus 1 by j omega l dv of z by dz is equal to right side is j omega cvz. J omega cv. So minus into minus is plus, d by dz into d by dz is d square by dz square. And the constants are 1 over j omega l into v of z is equal to j omega c into v of z. So taking this towards right, we can write d square v of z by dz square is equal to j square omega square lc into v of z. J j square is minus 1. So therefore we can have d square divided by dz square plus minus omega square is dz. So we got an expression for the along solution of us given by the solution is equal to constant E0 power j omega root delta t. So here omega root delta t acts as the phase constant. Power minus j beta z. So here phase constant beta equal to omega into minus t. So similarly, we can get an expression for I alone. So for that, we have to substitute we have set from equation number. We have set it equal to minus 1 over j omega c into derivative dz, and that value we have set as substituted in equation number 1. So we will get an expression for I alone. So that is a number we will do that, and we will get d square I is set by dz square equal to minus omega square I is set. Similar equation like this. We have similar equations for the right. The solution I is set I0 to the power minus j beta z. Beta is equal to omega root c. Substituting value of L and C. So we have already known that L is equal to d by w, and C is equal to epsilon w by d. So epsilon w by d. So the w's will get cancelled and w's will get cancelled. And beta is equal to omega root epsilon. And now we have to get the relation between dz and iz. We know that dz by iz is equal to dz is b0 e to the power minus j beta z, and iz is I0 e to the power minus j beta z. Is equal to b0 divided by I0. So now we have to get the value. The ratio of V to I is called the impedance of the medium. That's zero. It's called Z0. And we have to calculate the value of Z0. So we know that for that we have to use the transmission line equation, any of the transmission line equation. V or I. Here I use the transmission line equation. V is given by minus dV z by dz is equal to j omega L iz. So substitute over here, we will get minus d by dz of b0 e to the power minus j beta z is equal to j omega L I0 e to the power minus j beta z. The derivative here is minus j beta times b0 e to the power minus j beta plus b0 e to the power j beta e to the power minus j beta z equal to j omega L I0 power minus j beta z. J e to the power j beta z cancelled, and we have b0 by I0 is equal to omega L by beta. So now substitute the value. Omega L by omega is equal to cancels L by root L from value of the impedance of the medium. Z0. Z0 is equal to root of L by C. We can substitute the value for the inductance per unit length L and capacitance per unit length C. L is equal to mu into D by W divided by C as there is a root over here. C is equal to epsilon W by D. So this is equal to mu D by W into D by epsilon W. So we have a D square by W square and root of that is D by W into root of mu by epsilon. Mu by epsilon is the intrinsic impedance of the medium. So the impedance Z0 is equal to D by W times the intrinsic impedance of the medium. The quantity Z0 is the impedance at any location of an infinitely long transmission line. Infinitely long means it's very long and there is no reflected ray, only incident wave is there. E to the power minus kV. The positive z direction will travel in the market. A finite transmission line ആണെങ്കിൽ അതിന്റെ എന്ത് വെച്ചിട്ട് റിഫ്ലക്ട് ചെയ്യും. അതുകൊണ്ട് തന്നെ അവിടെ e to the power plus kV. Here we have considered an infinitely long transmission line. So that means there are no reflections. So Z0 is the impedance at any location that look towards an infinitely long transmission line. So Z0 is also called the characteristic impedance of the medium. So if the line is finite, then the ratio of V of Z to I of Z need not be Z0, but it is Z0 if that finite transmission line is terminated in Z0. And we have shown that for an infinitely long parallel plate transmission line with perfectly conducting plates and a perfect insulator in between them, and the plates are having with W and separation distance is D. Then the characteristic impedance Z0 is D by W times the intrinsic impedance of the medium. Now we have to calculate the velocity of propagation along the parallel plate transmission line. So that this is the phase velocity UK, which is equal to omega by beta, which is omega divided by omega root LC, 1 over root LC. So substituting the value of L and C, we can find that is 1 over root mu epsilon. So the velocity of propagation is same as that of the phase velocity of a transverse electromagnetic wave in a dielectric medium having permittivity epsilon and permittivity mu. So ഒരു unbounded mediumത്തിൽ phase velocity തന്നെയാണ് parallel plate transmission. Summarizing. So first of all, we have written the Helmholtz equation, and then we have written the expression for the edge. Then we have applied the boundary conditions to find out the surface current and surface charge densities of the medium. Then we have written the Maxwell's curl equation for the prime harmonic case, and since the electric field is having only one component and the magnetic field is also having one component, we have simplified del cross E and del cross H. And then we have integrated the expression for Maxwell equation for electric field from 0 to d over the variable dy, and we have integrated the expression for h, curl of h from 0 to w with respect to the variable x. While integrating, we introduced two quantities for the transmission line: the capacitance per unit length epsilon w by d and the inductance per unit length mu d by w. So this is having a unit farad per meter. This is capacitance per unit length, and this is having a unit Henry per meter. And we got these two quantities, and we also got the time harmonic transmission line equations, which is a coupled equation in V and I. Then using that two equations, we decoupled and then we got an equation for V alone and I alone. We have written the solution. That means the expression for V and I. V equal to V0 e to the power minus k beta z, and I equal to I0 e to the power minus k beta z. So, and we also have find out the ratio P by I, which is nothing but the characteristic impedance of the medium, and we also calculated the phase velocity, and we found that this phase velocity is same as that of the phase velocity of the transverse electromagnetic wave in an unbounded medium. And we also found the transmission line equations, which are given by minus d v of z by dz is equal to j omega L I z, where L is the inductance per unit length, and the second transmission line equation is minus d I z by dz is equal to j omega C v of z. So these are the two transmission line equations, where C is the capacitance per unit length, and L is equal to mu into d by w, and C is equal to epsilon w by d. And please show that mu into d by w is having a dimension as that of inductance per unit length, and epsilon w by d is having a dimension as that of the capacitance per unit length. So this is the homework. Okay.